Okay, I am looking at what the watts input is from the battery into the H switcher controlled by this spinning timing disc. Okay, so here's what it looks like on the scope. Notice it's all positive pulses because it's coming straight from the battery. There is no negative pulse being shown, but that is what's happening going into the primary because I have an H switcher. It switches this way then the other way, but I'm checking current before it gets switched, just coming directly out of the battery. Okay, so it has these pointy looking amps. This is current. The voltage is 12 volts, so I don't have the voltage being shown. And it looks to me like it's like from from here to here, or from here to here, it looks like about 7 milliseconds. Is that right? We have it on 5. The time division is 5, so each of these squares is 5 milliseconds. So I'm saying it's 7 from here to here. And it looks like about 20 off time from here to here, which is like 4 square divisions. That's what I'm seeing. You can stare at it for a while too. But it looks to me like it's 7 milliseconds on, 7 milliseconds on, with in between 20 milliseconds. So 7. And now one cycle, I'm going to change this now to here. Now one cycle would be a positive pulse, and then a negative pulse, and then another positive pulse. So what you'd be looking at for one cycle is from the beginning of this one, this would be a negative, and then the beginning of that one. And actually what I did is I just added it up. Let me put this back where it was. So I just added it up here. What you see on the scope, 7 milliseconds here, 7 milliseconds here, 20 here, 20 here, and there's the cycle. So 7 plus 7 is 14, 20 plus 40, so it's 54 millisecond cycle. Okay, just looking at it like that. And now, because these are triangles, what I do for that is imagine it, I make it an imaginary square wave pulse. And if you do that, this will be the same amount of space, or whatever it is, as this. So in reality, if this is 7 milliseconds, you would divide by 2 to figure the actual time. I guess that's the word I was looking for instead of space. So we're looking at the time period. So the time period of actually current being created or being pulled from the battery is half. So if I say 7 up here, it's really 3.5 milliseconds you'd be saying, in 3.5 milliseconds. So that means the on time is only 7 milliseconds in reality, while the total cycle is 54 milliseconds. And 7 divided by 54 is 0.13. Okay, so now when I went to figure the amperage, you see there, I have the square division in 0.05. And so 0.05 divided by 5, because there's 5 little spaces inside the square division, minor divisions you could call them. So I see 15 from the peak to the zero line. Okay, so we're in the 0.05 square divisions divided by 5 gives you 0.01 per space. 0.01 times 15 peak to zero line means 0.15. And it has a 0.1 current shunt, so it's 1.15 amps. And that's about what it shows on an ammeter. Now I know it's 12 volts, so times 1.15 is equal to 13.8 VA, I guess you'd call it, I don't know, joules maybe. And it's this is what you get, volts times amps, before you times it by 0.13, because that is the percentage of on time. .8. I have 13.1. Whatever. So it only is 1.7 watts in, according to these measurements, while it was outputting a lot more than that across that resistor. I can't remember what it was putting out. Just 1 minute. Okay, the output across the resistor is 67.3 volts. It's getting quite hot. 456 ohm resistor. So I'm going to do the math really quick for the output. Okay, for the output, 67.3 times 67.3, you square it, what the voltage is across the resistor, and it's a 456 ohm resistor, and that gives you 9.9 watts out. Now, if you took a meter and you measure what is coming out of that battery in current, what's being drawn, it's going to say 1.15 amps. And it's going to be a 12 volt battery, so you're going to say that it's 13.8 watts out. But in reality, for a 54 millisecond cycle, it's only drawing current for 7 milliseconds in reality. And the current it draws has a peak in 0.05 square divisions. It has 15 spaces peak to zero line, so that's 0.15 times the current shunt of 0.1, so it's 1.15 amps. And that is what it pretty much shows on a meter right there, being drawn from the battery. And we know it's 12 volts. So we have this as what you would consider to be the watts output, but it's really the volts times amps before the on time correction, I guess you'd call it. And it only comes to about 1.7 watts. Let's say it's 2 watts. Let's say it's 4 watts. It's still pretty good. So here again is what's coming out of it. 67 volts across 456 ohm resistor. Here again is the scope. Let's try it. And my scope is in 5 milliseconds. Each of those squares is 5 milliseconds. If you want to stare at this for a while, you might get what I got. And the one thing I did that's maybe not arguably the right thing to do, but I think it is, but then what do I know, is the scope forms, you make an imaginary square wave with them, and that means you get to subtract half of what the time is. So it's like really the on time is right here, not all the way to here. Okay, so there's some math to confuse everyone. And any comments, leave them down there. And thanks a lot for watching.